Hello, this is the first lecture for Chapter 4, Solution Stoichiometry, which is about stoichiometry that takes place in solution. And so we will be talking a lot about molarity and using the molarity equality for some of our mathematical stuff. A lot of what goes on in solution is involving water and electrolytes, so you need to sort of understand what goes on when you dissolve things. And the most important thing to remember is that water is polar, which means that it's got one side that is negative and one side that is positive. That comes from its bent shape, its two lone pairs of electrons, and the strong electronegativity of the oxygen compared to the hydrogens. So the oxygen ends up being partially negative in charge, and the hydrogen sides are partially positive in charge. Because the water is polar, if you throw an ionic solid in there that is actually soluble, each individual ion of the salt will be surrounded by the water molecules, and if it's a positive ion, it's getting surrounded by the negative side, the oxygen side of the water, and then if it's a positive ion, it gets surrounded by the negative side of the water. Did I just say that twice? Switch it, it'll be great. That's hydration, and that is the process by which each of the individual ions gets pulled off of the salt cube or the copper chloride or whatever that you just threw into the water. All of those dudes are called electrolytes because they are charged ions that are in water flowing around. You can conduct electricity because that's what electricity is charges that move. Soluble ionic substances, when they dissociate in water, mean that you've got water that can conduct electricity. Usually people think of pure water, as being able to conduct electricity, but it kind of can't really. But that's fine because we don't really ever run across pure water. There's always small amounts of ions dissolved in the water. Especially in swimming pools. But it's so clean. You've put yourself in there. It's not clean anymore. Are you saying I'm covered in salt? Well, yes. Strong electrolytes versus weak electrolytes. This is the difference between how much they will dissolve. A strong electrolyte is one that completely dissociates in the water and has a high solubility, whereas a weak electrolyte, you can throw that in there and it doesn't dissociate 100%. One example is, and those are typically not ionic compounds. Those would be covalent compounds that have like a loose hydrogen, say. So, for example, acetic acid vinegar. Only about 5% of acetic acid dissociates the hydrogen ion in order to make it acidic. And that is actually a covalent bond that breaks. So vinegar is a weak electrolyte, so it conducts electricity a little bit, whereas all of the ionic stuff that dissolves is going to be a strong electrolyte. You can measure the conductivity, and it's directly related to the number of dissociated ions. We kind of learned about this when we were doing colligative properties and like freezing point depression and boiling point elevation. This was the I, which is how many ions do you get out of each dude. So for sodium phosphate, Na3PO4, you've got 3 sodiums and a phosphate, so you've got 4 ions total. Whereas if you had just sodium chloride, you have 1 sodium and 1 chloride. So you've only got 2 ions per dude. So if you put in, if you had 1 molar sodium phosphate, that is way conductier than 1 molar sodium chloride because you just have twice as many ions. And it's also important to remember that acids and bases are electrolytes. So they conduct electricity because you've got hydrogen ions, H pluses, or hydroxide ions, OH minuses. And when I say something is a strong acid or a strong base, it means that they are strong electrolytes. So they dissociate 100%, whereas weak bases and weak acids are going to be the more organic acids and ammonia type based organic bases, and they have got smaller percentages that dissociate. All right, that's box 1. Box 2. You remember molarity, hopefully, which is the number of moles of your solute over the liters of solution. The good news is that they cut molality from the AP exam this year.
They did.
They did. It's gone. So,
Alright.
we're not doing it. So this one is the normal one, so that's nice. So moles of solute over liters of solution. Sometimes you end up having to do a mole of solute over 1,000 mils of solution in order to make things cancel when you're using this equality, so be aware of that. And let's see, here's an example. If you're talking about the molarity of a specific ion in solution, you have to be careful, because if you have 1 molar potassium phosphate, the concentration of potassium ions, there should be a plus there, is not 1 molar. It's 3 molar.
No.
Because there's 3 potassiums per mole of potassium phosphate. So you have to take that into account if you get a specific question that's like, what's the concentration of this ion? Make sure there's not 2 or 3 of them per dude. And then the dilution formula, M1V1 equals M2V2, which is your first molarity times your first volume is equal to your second molarity times your second volume. And you just got to make sure that your volumes are the same unit. So if it comes in mils, make sure you get your answer in mils. And that is how you dilute a solution. There's a couple more mental steps to it, because sometimes they'll ask you a specific question like, how much water do you add? As opposed to, what is your final volume? So you need to be careful with that. All right. You need 100 mils of 0.5 molar HCl. You have a lot of 6 molar HCl. What do you do? All right, let me go to the black pen page. You have 100 mils. Is that what I said?
Yes.
2V2. You need 100 mils of 0.5 molar HCl, so that's... No, that's not it. The molarity is 0.5. The volume is 100 mils. And then what I have is 6 molar HCl. And then we don't know V2. So that's 50 over 6 equals V2. And what's 50 over 6? I don't have my calculator up here. No, it's in the bag. I'm going to pause. 8.33. All right. So 8.33 mils equals V2. Now, the question said, what do you do? 8.33 mils is not an answer to the question, what do you do? So be careful the way they're worded. What you do is you pour 8.33 mils into a 100 mil flask, and then you fill it up with water to the 100 mil mark. And so another question might be, how much water do you add? Well, you need to get to 100, and you started with 8.33. And so you have 91.67 or whatever mils of H2O. So just be careful with the wording of the question and your answer. Right. And the next thing is the solubility rules, which is usually considered to be kind of the most horrible thing you have to memorize ever. But I have a thing that makes it kind of the best thing that you have to memorize ever, so you should be happy.
Yay!
All right. There are many ionic compounds that dissolve in water, and there are many that do not. There is kind of a list of rules that allow you to determine just by looking and remembering your rules, okay, yeah, that's clearly insoluble, but that one's soluble, and it just allows you to know what's going to happen in a reaction, whether you're going to get a precipitate out when you're doing a double displacement reaction, which ends up being important with a double displacement reaction. If you, we talked about the net ionic equation. When something becomes a solid, then that's a reaction. And so those ions do not get canceled out in the net ionic equation, they stay. Whereas the other ions do. So if you think that something stays soluble, you will cancel it out. And if you're wrong, you weren't supposed to. It was supposed to be the reaction. One clue is if they say, what's the net ionic reaction? And everything cancels out, then you probably missed something. Yeah, so this is important for you to be able to predict whether a precipitate is going to form. And also be able to predict, if I throw this in water, will it help? Which is kind of an important lab skill, because I will often be like, does this dissolve? And then I know, because I know the rules. So here's the rules. There are characters that represent different ions, and the characters kind of have a story and personality traits about them. And what you need to know is, if a character is a good character, then they will dissolve in water. If a character is an evil character, then they are insoluble and they will not dissolve in water. So let's go to the medieval solubility tale. So this was written by Mrs. Kelly Schuler and her AP Chemistry students. Typically, you are given a list that looks like this and just told to memorize it for AP Chemistry, which is sad, because look at that list. Isn't that terrible?
Yeah, it's daunting.
I don't like it. It's really easy to forget pieces of it, and then you make that mistake, and then you get the equation wrong. So what's nice is we can learn this with just a few characters and a few personality traits. So here come the characters. We have some good guys and some bad guys. The good guys obviously include the Pope.
All right.
He's not evil. He's great. The Pope is comprised of the alkali metals, so sodium, lithium, potassium, rubidium, those guys. So that's the Pope. And he also has got some minions. Maybe they're monks, let's say. He's got some minions that help him, who also qualify as members of the Pope team. And that is obviously the NAACP. They help the Pope, right? And that's an acronym to help you remember that nitrate, N, ammonia, the first A, acetate, the second A, chlorate and perchlorate, chlorate and perchlorate. I'm thinking that maybe NAACP is the National Association for the Advancement of Chemistry Professors.
Yes.
So the Pope always wins. If there is a Pope present in the ionic compound, it is good. It will dissolve in water. So nothing can overpower the Pope. The next character that you have is Good King Halide. And obviously, Good King Halide is comprised of chlorine, bromine, and iodine, not fluorine. Fluorine tends to be sort of insoluble in many cases. So Good King Halide is chlorine, bromine, and iodine. And the thing about Good King Halide is that, well, we'll have to get to the witches in a minute.
There's witches?
There's witches.
Are they good?
No. So that's Good King Halide, and we also have his young, beautiful wife, Queen Sulfate. And she is good as well, but she also has weaknesses that we will discuss when we have met the bad characters. So the bad characters are insoluble, and you've got a bunch of different polyatomic ions. 1, 2, 3, 4, 5, 6, 7. 7 of them, and that are the main ones that pop up that are insoluble dudes. So if they're present, generally it's insoluble unless they're overpowered by the Pope, the King, or the Queen. So the group wizards include sulfide, oxide, phosphate, the 2 chromate ones, chromate and dichromate, carbonate, and sulfite. That is a list that you're just going to have to memorize. Maybe you can make an acronym for it. I don't know. We'll figure it out. So those are the group wizards. There's a special wizard, which is the hydroxide wizard. And he has got a weakness that we will discuss as well. But in general, things that are hydroxides will not dissolve unless they're overpowered by the Pope, the King, or the Queen. And then the three witches, the names of the witches are Ag, Hag, and Pib. Are also evil, and so if they are present, in general, you've got something insoluble, but they have a weakness. Well, no, who has a weakness? Ag has a weakness as well, so we'll get to them. All right, next one. So the good guys. Here is the Pope. I couldn't do my job without Group 1 and the NAACP working for me. Here is Good King Halide. Hello. I think this is a picture from like medieval times, maybe. And here is young, beautiful Queen Sulfate, who is usually good. But what you have to know, let's see, here's Ag, Hag, and Pib. The group of wizards, which are sulfate, oxide, phosphate, 2 chromates, carbonate, and sulfite. I remembered them.
Well done.
And the hydroxide wizard. Now, for the weaknesses. The Pope does not have weaknesses. If he is present, it is soluble. So potassium is a Pope. This is soluble. Potassium bromide is soluble. Ammonia is from the NAACP, soluble. Iron generally would be insoluble, except we've got chlorate here. Chlorate. And so that's a Pope, and that makes it soluble. Soluble for sodium, even though carbonate would typically be insoluble, the Pope overpowers it. Acetate from NAACP, lithium overpowers the hydroxide wizard, and nitrate overpowers manganese. So that's the Pope. Those are examples of. So now we know that all of these are soluble, just because we know that the Pope is good and he's made of these guys. So, all right, next we have Good King Halide, who is chlorine, bromine, and iodine, not fluorine. And so you end up with, chromium chloride, that's soluble. Zinc bromide, that's soluble. Ammonium chloride is obviously soluble because you got a Pope and a King. But here's the thing: the witches can overpower the King with an evil spell.
Uh-oh.
I know, right? So Ag, Hag, and Pib, which is silver, mercury, and lead, combined with Good King Halide, end up being insoluble. So silver bromide is insoluble. Mercury chloride is insoluble. And so would lead chloride be insoluble. So Good King Halide, generally good, can be overpowered by witches. Next. Go back one. Beautiful, young Queen Sulfate. Apparently you have to say beautiful, young every time. I'm not really sure. All right, here's the thing. So for example, we've got potassium sulfate. She's usually good. Potassium's a Pope anyway, so this is soluble. Ammonium sulfate, totally soluble. Pope and Queen. She has got the problem with the witches as well, except it turns out that Queen Sulfate and Ag are sisters. Look at them. They're both blonde.
All right.
So
That's
while
sisterhood.
I know, clearly sisterhood. So while Hag and Pib can overpower Queen Sulfate, her nice sister doesn't. So silver sulfate is soluble. It's still good. So there we go, silver sulfate here. Whereas mercury sulfate is insoluble and lead sulfate is insoluble. Now, she has a weakness, like a personality flaw. She has this tendency to, instead of being in the castle when she's having kind of a low day, she tends to go to a cave and smoke a pipe full of strong tobacco, which is strontium, barium, and calcium, strong tobacco. So when she is smoking, she's evil, obviously, smoking being evil.
Very evil.
So when you end up with calcium sulfate, tobacco, calcium sulfate is insoluble.
Okay.
Zinc sulfate is soluble. Barium tobacco is insoluble. Iron sulfate is soluble. Here's ag,
Soluble.
is soluble because that's her sister. Copper sulfate is soluble, and strontium sulfate is insoluble. Yep. So there we go. There's queen sulfate. Next. And then here is the wizards in general. Which if you just remember the 7 wizards, as long as they're not overpowered by the queen, the king, or the pope, it's insoluble. Now the thing about the hydroxide wizard is that he has a weakness for being nice. Because, if you're the queen and you smoke strong tobacco, that makes you evil. But if you're already evil and then you smoke strong tobacco, then you become nice. So he's thinking, ooh, that strong tobacco makes me feel so nice. So that gives us the ability to do these, which is lead carbonate, insoluble. That's a witch and a wizard. Iron hydroxide, insoluble. Zinc sulfide, insoluble. That's one of the wizards. Sodium oxide, there's a pope, soluble. Potassium nitrite, soluble. Magnesium nitrite,
Insoluble.
yeah, I'm saying that's insoluble because that's not nitrate. Calcium hydroxide is soluble because this is the hydroxide wizard who's typically evil becoming good because he's smoking. Barium sulfite, that's a wizard, so that's insoluble, but barium sulfate, that's queen sulfate with barium tobacco, so this is insoluble again. Barium hydroxide, the evil hydroxide wizard overcome by nicitude, so that's soluble. The phosphate and calcium, that's insoluble, and then here's a pope, so that's soluble. Whew. That is it. That's the whole thing. You've got 4 or 5 characters, good or evil. Now you know whether anything is soluble or insoluble if you can just remember those things. And that's sort of a fun way of doing it instead of a horrible, torturous way. So hopefully you've been taking notes and filling in these little lines here. If you haven't and you need a moment, pause and fill them in. All right, the next thing is titrations, which we talked about briefly last year. We are going to do an oxidation reduction titration lab soon, after we learn about oxidation reduction on the next lecture. And then when we do acid-base in the spring, we're going to do actually a couple different acid-base titrations. The idea is you're trying to figure out how much of something is in an unknown solution by dripping it into, by dripping something that you do know into it, and then it changes color at a certain point, and then you're like, hey, that was how much was in there, because they perfectly neutralized. With acid-base titration, you're trying to figure out, for example, let's say you have an acid and you don't know its concentration. You go, okay, well, I'll drip a base into that acid. I know the concentration of the base because I got it out of my labeled bottle. And then right when it neutralizes, it will change color to pink. I don't know, make up a color. And then I will be able to go, oh, that was 35 milliliters of 3 molar base. So that means that was this many moles of base, which is that many moles of acid. So that was the concentration of the acid. Ta-da! It's kind of how it goes. And you can do that with acid base or oxidation reduction. So the couple of things that are important, there's a couple of words. The glass thing that you drip with is called a burette. The stuff that you are dripping in is called the titrant. The stuff that you are dripping into and analyzing is called the analyte. And then there's two things that you need to think about when you're deciding when you are done. You want to stop dripping when the amounts are equal. That's the overall goal of the experiment, because then you can go, okay, the amounts are equal. I will stop. Now I will do math, and then I will know the answer to how concentrated it is. That point is called the equivalence point. They also call it the stoichiometric point, the point where the amounts of the dripper and the catcher are equal. You have to set yourself up ahead of time so that you will know when they are equal. You need to get some indicator and put it into your analyte so that when the amounts are equal, the color changes. Because otherwise you're just like drip, drip, drip. Am I done? I don't know. This way you go drip, drip, drip. I know I will be done when it turns blue because I chose an indicator that would turn blue when the pH was 7, and when the pH is 7, that's when it's neutralized. That point is called the end point. That is when you should end. Whoa. The point at which you should end. And because you are the person who is choosing what indicator to put in, you can screw that up. So if the amounts are equal at pH 7 and you put an indicator in that turns blue at pH 5, you're going to go drip, 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 drip. Hey, it's blue. I'm done. Let me do my calculations. But they will all be wrong because the amounts are not equal. Because you were supposed to wait until pH 7. But it turned blue. Well, it turned blue because you put the wrong one in. So you have to choose your indicator properly in order to do one of these at all. So be careful about that. And there's a phrase that is related to titration, which is called standardizing a solution. Which is, here's a solution. And you go and you figure out what its concentration is using a titration. And now you have a standard solution. You have standardized that solution. You know its concentration. You could theoretically use it as the titrant in future titrations. So if you ever see a question that says, you've standardized the solution, what does that mean? It means you figured it out. And now is the time to pause the video and go and do the questions on the back of this page. All right, here's your question. Classify the following as strong or weak electrolytes, which would be the best conductor of electricity. You have to remember that all of the organic dudes are terrible electrolytes. So this one, which is organic, is not a good electrolyte. This one, which is organic, is not good, not good. So those are all weak. Also, bases based on ammonianess are weak. So that leaves us with hydrochloric acid, which is strong. Magnesium chloride, which dissolves because of king halide here, is strong. Oh, here's an organic one. Weak. Here is beryllium hydroxide. Hydroxide wizard means it doesn't dissolve well, so that's going to be a weak electrolyte. And sodium, that's S is for weak. And here's sodium phosphate, which is strong because of the Pope. And your best conductor of electricity is going to be the one with the most ions per dude, which is sodium phosphate, because you get 3 sodiums and a phosphate. All right, calculate the molarity of a solution containing 5 neener grams of iron 3 chloride and enough water to make 250 mils of solution. That's going to be, you need to figure out how many moles that is. So 5.05 grams of iron 3 chloride. Bring down your unit. And the molar mass, I have 162.2 per mole. Giving me 0.031 moles. Iron 3 3 chloride. And with 250 mils of that, you've got to remember that the molarity is moles over liters. So that's going to be this many moles divided by the number of liters that 250 is, which is 0.250 liters of solution. And you divide that out and you get 0.12 molar iron 3 chloride. And then what is the molarity of chlorine in that solution? You need to remember there's thrice as much chloride as there is iron chloride. So that's going to be 0.36 molar. Okay, that's 1 and 2. 3. This is a double displacement reaction. You've got sodium chloride aqueous combined with mercury nitrate aqueous. When it says aqueous, that means that it's dissolved. So this is soluble, and we know why, is because we've got nitrate here. That's a Pope. And this is going to be a double displacement reaction because there's not really anything else to do. And you're going to have a precipitate that falls out of solution because otherwise it's not really a double displacement reaction. It's just a mixture of salt. Of two different random salts that don't interact with each other. So what you can get is you can get sodium nitrate, which is so soluble. It's 2 Popes. And you can get mercury, which you've got to remember that the mercury ion likes to hang out with itself. So mercury tends to come in pairs, Hg2, 2+. And that's going to result with you being Hg2Cl2. That is king halide with Hag. So Hag makes him a solid, whereas sodium nitrate is aqueous. If you're going to write this as the net ionic equation, first you would balance it because you're a good person. There we go. If you're going to write this as the net ionic equation, the sodium and the chloride and the Hag and the nitrate, 2 of them, yields 2 sodia and 2 nitrates. And this one does not show up as broken into ions because it is a solid precipitate. So it goes together and you cross out the dudes that are the same. And so what's funny is it goes, look, when you combine chloride and mercury, you get mercury chloride. Woo! All right, this one you end up with calcium carbonate, which is a solid, and sodium hydroxide, which is aqueous. And in terms of balancing, 2 of you, and that's beautiful, isn't it? Yep, that's beautiful. So if this was net ionic, you would cross out the sodiums and the hydroxides and just end up with this dude. And thirdly, we have sodium chloride and iron sulfide, which is Fe2S3. So iron 3 sulfide, this is going to be your solid precipitate. This is going to be aqueous. And if you were doing the net ionic, you would cross out the sodiums and the chlorides. All right, 4.
Do you need to balance it?
Yes, I need to balance it. Do you need to balance it? She asks tactfully. Thank you, assistant.
You're welcome.
I need, ooh, a 2 and a 3, huh? I'm gonna need 6. 3 and 2. There, are you happy now?
Yes.
Good.
Thank you.
All right, how many mils of 2.3 molar nitric acid is needed to neutralize 0.92 liters of 0.5 molar KOH? That's going to be the first instance of using that new equality that we haven't used a lot. And what you need to remember is when you're using the definition of molarity equality, you're typically starting with this structure, which is, and since this is in mils, I'll just switch it to mils, 920 mils of KOH solution over 1 times your definition of molarity equality. Mils of KOH solution. And we ask ourselves, what do we know about a certain number of mils of KOH solution? Is that 1,000 mils contains 0.5 moles of KOH. That will get you the number of moles of KOH that you have. And that's going to give you 0.46. I calculate 0.46 moles of KOH. Now, this being a base, if you're going to neutralize, and this being a monoprotic acid, you end up with, those guys will neutralize when you have equal amounts. 0.46 moles of HNO3 would neutralize 0.46 moles of KOH. So how many mils of that do you need? Then you're going to go, okay, well, I've got moles and molarity, and I want mils. That's molarity equals moles over liters. So that's going to be, what's my molarity? 2.3. Thank you. 2.3 equals 0.46 over liters. And so liters ends up equaling 0.2, which is 200 mils of what? Of 2.3 molar HNO3. Beep. Box. All right. And number 5. It took 18.96 milliliters of 0.150 molar hydrochloric solution to titrate 25 mils of ammonia solution. What was the concentration of the original ammonia solution? Again, you're going to be starting with milliliters of solution. So you've got 18.96 mils of HCl solution. Why don't you draw? There you go. And you bring that down and you go, what do I know about mils of HCl solution? I know that in 1,000 mils there are 0.150 moles of HCl. And that gives me 0.002844 moles of HCl. That's not much, it's true. But we are only dealing with small numbers of milliliters, so don't be too surprised. In order to titrate an acid with a base, these are all one. This is a monoprotic acid again, so you don't need to worry about doubling anything. That many moles of HCl is going to be that many moles of ammonia that you neutralized. And then what was the concentration of the original ammonia solution? That's going to be moles over liters, which 25 mils is 0.025 liters. And that gives you 0.11 molar NH3. Bam. That's it. Bye.